One of the important areas in which model interpretability should have an impact, I guess some would argue the most important area, is in healthcare. After all, what good is some black box? Well, it's worth something if it's reliable, but yeah, better than a black box would be a transparent box. And while that makes a great pull quote, easier said than done, there's also an interesting aside here about interpretable for whom, patient or doctor. And my concern is doctor, because the last thing I want are patients self-diagnosing and getting access to AI tools to essentially make the sort of inferences that you need a guided, trained eye to make. So in my mind, success of applied machine learning and healthcare is really about helping the doctors, the clinicians, the radiologists, the people that are operating the machines and interpreting the evidence and doing that sort of thing. So surely there's some interesting work specifically on model interpretability in the context of healthcare, right? This week on the show, I speak with Jay Thiagarajan about his recent paper, Calibrating Healthcare AI Towards Reliable and Interpretable Deep Predictive Models.
Hi, I'm Jay Thiagarajan. I'm a computer scientist at Lawrence Livermore National Labs, and I'm with the Center for Applied Scientific Computing division there doing research in machine learning and artificial intelligence.
And I'd asked you on today, most notably, to discuss your recent paper, Calibrating Healthcare AI Towards Reliability and Interpretable Deep Predictive Models. This is right at the intersection of the things we like to get into here. It's interpretability and ML. I'm not an expert in healthcare, and I know it does take some expertise. Can you tell me a little bit about your background and how you've learned these two fields and whatever their overlap is?
So my background, my PhD was in machine learning and signal processing, being applied to a variety of problems in computer vision. However, when I started working on applying AI tools to several real world problems, Livermore being a science lab, we typically focus on a variety of scientific applications in which data driven modeling could be potentially used. And that's where I started working on this general space of biomedicine where healthcare analytics forms a part of it. And I've been fortunate enough to work with collaborators who have been teaching me cool stuff while I was completely illiterate beyond my basic biology classes at school. So I started learning as I started working on these projects, and my awesome collaborators, including the ones at IBM Research and other places that I work with, they've been helping me get on top of some of the important challenges the field faces and how we could potentially repurpose some of these cool tools that we are building in general AI and vision problems to problems specific to healthcare.
I see a lot of headlines that brag for certain problems, like maybe it's radiologists and things like that, that algorithms are now achieving these human level performance. Although when you look a little deeper, maybe that's perhaps a stretch. What's your perspective on the current state of the art in computer vision? How close are we to that human level goal we're all seemingly after?
I think that that's a very philosophical question at some level, right? If you actually talk to a doctor, there are definitely tasks in which AI tools are producing human level performance, okay? But if you deep down, if you go to the doctors and ask them, are those the tasks that you really want AI tools to help you with? Many times the answer is no. The kind of problems that the actual doctors and people who are treating very, very difficult infections and diseases, they are looking for is to solve really, really challenging problems, which often do not cut into the benchmarking statistics that we typically build in the vision community. So as a result, what happens is even though we produce a lot of promise in kind of building diagnostic tools, they might not be directly impacting healthcare as the way immediately expected to. However, this conversation is starting now where a lot of more practitioners are getting involved in conversations with us. It's not anymore like we take an arbitrary data set and we just publish in our own computer vision and machine learning venues and the doctors don't look at it. So that is changing. So which means what is first going to happen is to define realistic problems that are actually going to have an impact, and which is not a very easy thing to do. You have these awesome hammers and we are looking around for nails, but however, this needs a more fundamental rethinking as to what healthcare problems need to be solved and which is the actual big challenge. And for example, we are surprised by something like a COVID infection, correct? Which we didn't even know what kind of data modalities could potentially even detect it well. And suddenly we are thrown into this pool where we are saying we need to find a screening mechanism and we need to detect things. And more importantly, they ask us, can AI tools be used in order to gain new insights that we do not know already? So in some sense, AI, if it is going to continue merely being an automating tool, then the future is not as promising. However, the entire field is moving past that. It's not just for making difficult jobs faster, but it is also doing tasks that are typically hard even for a human to solve in a day-to-day basis. And how do we enable them to do better? Sometimes it's not even replacing them and doing it in their place. And many times it's even assisting them to navigate through this really difficult problem.
And I presume assisting a doctor, if you just give them a black box model, maybe that's helpful, but could you talk a little bit about the value they get out of a model that also is interpretable?
I think here I have a personal understanding of this problem in general, and it's my own opinion about it, right? Many a time, people often equate interpretability to accountability, interpretability to being a model being responsible, or giving you a way to trust models, correct? Of course, they are loosely connected, but the underlying goal of interpretability is not that. So, interpretability, it is merely a means for a human expert who already knows really, really well about the problem to interact with this system in order to make sure the hypotheses they have about their field or about their problem is actually holding true in the model that we built. And more importantly, can you go a step further in order to form a relevant hypothesis? In some sense, it is just a lens in order to open into this black box, large scale models that we are building. And accountability, trust, fairness, all these related concepts, even though they are often put in the same bracket as interpretability, each of them is a separate problem on its own. Just because we make a model interpretable doesn't imply that we have made it fair. It doesn't imply that we have made it responsible, that now you can put it in a self-driving car and everything is going to be fine.
Sure, yeah, it could explain why it killed the pedestrian.
Exactly. So, in that context, in healthcare, the big challenge we are facing is that we are trying to interface with a human much more than many applications. And I funnily say this to my collaborators, and a lot of people resonate with this, is that many a times the interpretability techniques that we build, the kind of explanations that we produce, they might be more useful to another machine than to a human. So, for example, if I had a model and the model exactly tells you in many of the tools that we currently have, they produce these kind of explanations and modalities and stuff like that, it's extremely hard for a human to wrap around all that and obtain a holistic understanding of what is happening. A single explanation is not a description of how the model completely works. It's a really, really small fraction of what happens in a model. Consequently, the way the humans interact defines how you can understand about a model more than how sophisticated or clever your algorithm is. So I can build a really, really awesome interpretability tool and all visualizations, and I show it to a human. And if it is hard for them to wrap their head around it, it's not useful at all. In that sense, can we start thinking about new formalisms which will enable us in order to allow interaction from design? So that means we cannot design that unless we talk to the concerned practitioners and saying, how do they love to interact? How do they expect in order to use an automated machine like this in order to go about their work? So in that sense, we are trying to redefine depending on every. So there are applications where prediction alone is sufficient, where interpretability is not even needed. So I don't even prescribe interpretability as a list for every single problem we solve. It is very, very application specific. For example, somebody designing a drug will want to know not just what a new drug could be, but then if you say that I can predict this new drug, but the amount of effort that you need to do to synthesize that, if it means to conquer an entire city in order to do that, it's not useful, correct? There is a realizability conditions that come in and feasibility requirements that come in different applications. And there is a need in order to put all of these into this box in order to build an interpretability tool that is actually useful.
Yeah, very well said. Could we talk a little bit about the data set you used in the paper? What were some of its contents and what do doctors hope you can achieve looking at it?
So these problems are broadly in the space of diagnostic modeling, correct? Where the goal is to use whatever data modality you have. In this case, it happens to be images, but it can be any data modality that you typically obtain for a health record, for example. The goal is in order to perform some form of prognosis, correct? So where the doctor, even before they want to end up prescribing treatments or end up identifying what kind of tests that should be run. So this is a first step potentially, correct? Where the model kind of gives you a description of what might be happening with this particular subject. And in this case, for example, we are looking at skin lesions. And the way doctors have been traditionally building mechanisms in order to detect skin cancer has been skin lesions has been very, very heuristic in the sense that it's very hard to translate the knowledge and the decision protocol that a doctor uses into a machine learning model. For example, what they popularly call as the ABCD rule, which is asymmetry, border, diameter, and the color of the lesion in order to categorize what type of lesion it is. Is it benign? Is it going to be dangerous? So, what kind of treatment protocols that should be considered for that particular patient? And all that happens based on a very, very knowledge driven, experience driven diagnostic process. So, in order to translate some of that into a machine learning model, it's very, very tricky. So, that means even if I build a diagnostic model, at some point, the doctor wants to know, can you map whatever you are trying to predict? Can you map those signatures or features that the model actually looked at into something I understand? That means there is a mapping, there is a communication. So, what the model does is in a completely different language compared to what the practitioner does. For example, a doctor could look at 10 patients within a minute and quickly come up with an assessment of what could happen. But on the other hand, for a model, even if it makes predictions, in order to convince the doctor why it made those decisions, it's highly non trivial. So, this particular paper starts talking about how do we formalize this problem a little differently. There are two aspects that we are interested in here, correct? One aspect is that even if I treat it as a black box where the doctor does not want to understand every single nut and bolt of this model, they want to be sure that the model is actually reliable. And what do we mean by reliable? In a plain English way of putting it, when a model makes a mistake, the model better be not super confident about it. So I would rather have a model which says, I don't know what's happening here. Doctor, can you come in and take a look? Rather than the model saying, this guy has this type of cancer. I'm fairly certain. And the reality is that person is actually all right. So what happens in that scenario is there is a need to systematically trade off between model autonomy and its accuracy in the real world. And this should be evaluated on test data, on new patients that we have never seen before. And there is no way to systematically evaluate that. And how do we mathematically do this? And people in statistics have been doing this for a few decades now in their own ways before even all these advanced machine learning tools came out, which is called as uncertainty quantification. So it is basically the science of quantifying what variations that can happen in your predictions based on the uncertainties either in your data or your environment or the modeling assumptions that you have placed. So by systematically doing that, they provide you ways in order to calibrate the predictions that you produce from a model with what we expect in the real world. The larger the discrepancy between them, your accuracy number alone does not matter anymore. So you could be 90% accurate, and the 10% that you actually miss could be all cases where you are missing important diagnosis decisions. So these summary statistics that we produce are not sufficient anymore. But the other side of the picture is I have a reliability tool, maybe using these statistical principles. Can I somehow use it to interpret as well? Correct? Is there a connection between these two problems? And that's what this paper tries to explore by building a calibration technique, which kind of helps both reliability and interpretability being improved for these black box models.
Very neat. And is that calibration essentially a trade-off? Do I have to give up some interpretability to get accuracy?
So, in some sense, interpretability in this particular context, it's not like a self-explainable machine yet, where the interpretability is by design, they are evolving it as part of the model building process. So here, interpretability, I would rather call it as introspection, where there is an interaction involved there. That is still a post hoc process. The interpretability happens only after building a model. So consequently, reliability is the primary aspect. That's a broader goal. Once you have a reliable model, then the prediction uncertainties that you have, which is how confidence measures, is something we typically understand, and that's how we deal with in real world. And we have a way of understanding it, even though probabilities are complex. We have a sense of making decisions. If somebody says there is a 50% chance of raining, you already know whether to carry an umbrella or not, because we have enough experience in order to act upon these uncertainty estimates. On the other hand, interpretability tools are completely disconnected to this process, correct? Interpretability tools have been predominantly been solved only from the standpoint of opening black boxes. For example, in computer vision, we use gradient guided saliencies in order to understand which part of the image do you look at and quantities like that. However, what might be interesting will be to connect the notion of reliability that we produce in the context of calibration, and can you somehow tie to the interpretability tools we typically use? So that means there is no single explanation for any behavior of your model. It is about exploring. You exploring a sequence of solutions, for example. You explore a variety of explanations which collectively could give you a better insight into the model. So let me clarify this. So for example, if somebody asks you, can you tell me how a cat looks like? So one smart way to do it is you show one image of a cat and hoping that they already understand what cat means. Or you give a textual description of what features in a cat are, and that could be another level of information that you can provide. But the most interesting way to do it is if I can start giving you cats and I start telling you how different this cat can be, and potentially at some point of time when a cat turns into a dog. And now no more, there's not a cat, this should be a dog. So that's how we are typically taught, where we are taught by contrasting. We are taught by, in some sense, these counterfactuals. This is an important field of study in statistics, where they call it as a counterfactual reasoning, where they say a best way in order to reason about something is to produce alternate outcomes. In order to say, if you had done this, this would have happened. If you closed the schools in this period of time, we expect the pandemic to spread this way. So we have these what if scenarios for which we don't have data, but we have enough evidence in the data statistics that we have collected that we can potentially answer those what if questions. And this paper claims that we can use the calibration principle in order to drive such a counterfactual reasoning, which is what we use for the interpretation process.
Yeah, let's dive a little deeper on the calibration process. Could you talk about the degree to which that involves a user?
So it can involve users to a large degree, depending on what kind of real world prior that you want to place. But in this particular context, the calibration that we do in this particular problem is completely free of any user involvement in some sense. Because the kind of calibration that we are talking about here is called as interval calibration. By that, what we mean is we want to produce prediction uncertainties. That means you are not going to produce one decision for each sample. You're actually going to produce an interval of decisions. That means by interval, what we mean is I think this person has cancer with particular likelihood, but it is also possible that there are so many other things that could be associated with the same patient with this probability. That means it's not a single decision, you are producing a distribution of decisions. Now, when you have something like that, an important way in order to calibrate is how likely is a plausible or a feasible real world solution lies inside that interval versus a completely infeasible decision being included in that. For example, we don't want a prediction uncertainty which says this person has benign cancer with 90% probability, but its interval also contains, say, this person being completely healthy, in which case the model is completely unusable for people. Or, for example, in these real world problems, there are different types of cancer. If you associate the same patient with multiple types of cancers at the same time, then the treatment protocols are going to become extremely hard. So, what to calibrate is that. So, the model can be confused, but the model cannot be confused by putting in pneumonia and COVID infection together being likely chances, which do not really happen. So the whole point here is that the expected calibration is you trying to ensure the plausible solutions are included within your prediction interval, while the infeasible solutions are not. And we kind of drive this using a mathematical formulation, which directly allows you to optimize the calibration based objective.
Yeah, let's talk about that. The paper also entertains some more traditional techniques like logistic regression and random forest. And of course, the proposed technique outperforms those. Can you talk a little bit about how that interval allows it to get that improvement?
So there is one key component that the model begins by assuming before even starting this whole process. So this entire problem of counterfactual reasoning is under the hope and assumption that any counterfactual outcome that you produce is physically reasonable. So let me break this down. If there is an X-ray of a healthy patient, okay, and somebody asks the question, and I have a model that can effectively classify between infections and healthy patients, okay, and you ask the model the question, I give you a healthy patient's X-ray, can you now potentially synthesize a counterfactual for the same patient, which is another synthesized X-ray image, which progressively shows the person being infected, even though the person was completely healthy, correct? You are creating a counterfactual. Now, what you are basically enabling the model to is the model understands the distribution of the variations among patients who are healthy. It understands the variations among patients who are infected. Now you are trying to potentially synthesize new. So it's kind of a generative process. So generative models have become a very key component in machine learning these days, which, for example, in many computer vision applications, are used to synthesize real looking faces or to solve inverse problems. For example, somebody gives you a face and you mask a part of the image and you want to recover. And people have been using for those contexts. So here, what we are doing it is we are using generative models in order to help us in this process of synthesizing counterfactuals. So in particular, we are using what is called as a variational autoencoder, which is basically a statistical model which allows you to sample from a space of latent factors. By that, what it means is you give me a bunch of data, bunch of images, I identify the key degrees of freedom that explain all variations in the image, and you can sample from that space. That means you can create a new image, you can potentially alter a given image and interpolate between images. For example, you can change to a male face to a female face, and stuff like that. So now what we are showing here is that when you have such a latent space and all models are built on top of this generative model. So there is a generative model which knows how to synthesize things, and that's what we are going to use in order to synthesize all the counterfactuals. And we are building a calibration driven model which is basically built on top of these latent factors. So consequently, you can potentially build all these random forests or even conventional neural network based models, which first of all do not produce prediction intervals. They only produce point estimates. They just tell you this person has a likelihood of zero point 0.9 being infected or not. And the important criterion here we are measuring in each of these cases is we are measuring the reliability of these methods. By reliability, what do I mean? So this is what we are going to do. For every sample, the model needs to produce a confidence. It should not just say this is infection, no infection. It should also give you a probability. And now you take all samples, all patients, rank them by the confidence. Okay. When the confidence is really, really low, it kind of means that the model does not know what to do. It just made a guess. And let's assume that in that case, you bring in the doctor and say, these are patients that the machine could not do well on. So we give it to you in order to make the decision. Here we assume that the doctor is the oracle who always makes the right decision, which is difficult in many real world problems, but let's assume that. So even in such a scenario, what we expect is on all samples the model was confident on, it should do a really, really good job. And in the cases where it was not confident on, the doctor can help fill in the gap. The doctor and the model collectively sit together and make the best decision system out there, which is what we call as a reliability plot in this paper. So where there's a figure where it kind of shows where in the x-axis, we kind of show percentage of the patients that we defer to the doctor, that the doctor needs to look at. On one end, in the extreme, you can say the model can send every patient to the doctor saying that I'm not confident, in which case there is no use of the model. In the other extreme, you can go to the other side and say the model autonomously makes decision on everybody, even when it's not confident, which is very dangerous because there are regimes where the model is not good, which needs to be taken into account. So what we do is we try to trade off between these two extremes based on the confidence estimates the model produces. So the accuracy is one statistic. The accuracy that we typically measure is in the extreme scenario where the model is completely autonomous. However, what we are interested in a real world healthcare setting is that trade off where I'm ready to give up some amount of autonomy if the detection performance can be significantly higher. So, in that sense, what we find is compared to any model that we currently use, bringing calibration into the process makes the reliability plot look much, much better. For example, you can reach 5 to 10% higher detection performance by just deferring, say, 10% of the samples to the doctor. So 90% of the cases, the model always makes the decision. This makes the AI system a more realistic thing, right? Instead of saying the AI system automatically matches the human performance, which is an overly optimistic understanding of this autonomous system. So this allows you to trade off. And we believe something like this should be part of every single diagnostic evaluation that needs to go out in the future, which gives a realistic picture of how good the model is. And that's where it becomes much better than any of the existing tools that we use.
Those latent parameters, I'm familiar with applications of methods like that and variational autoencoders and things like BERT and natural language processing. And my experience has been those latent variables, there's no guarantee that I can interpret them. In fact, usually I cannot. What do you find in your application?
So no, we do not. So in fact, we do not try to interpret those latent variables in any way. So we only use those latent variables in order to run this counterfactual generation process. That means instead of directly manipulating the image pixels directly, which is a very, very difficult job, particularly in an X-ray image or these medical images, because there are subtle variations that can change your prediction completely. So there can be some characteristics which make it benign, some characteristics will make it dangerous. So in those scenarios, what we do is instead of we interpreting the latent factors directly, we run an optimization saying that by ensuring that the decoder or the generator, so an autoencoder is a variational autoencoder is a combination of two components. There is a generator component, which is you give me a point in the latent space, it can produce an image for you in the X-ray image space that you actually can understand. So what we actually do is we allow the calibration process in order to search for an appropriate latent space representation, which can then be transformed into an X-ray image for the doctor to actually look at. So the doctors do not actually have to look into the latent factors. They indeed look at the reconstructed X-ray images. For example, what we find is if you take a type of skin lesion and it was called as a certain type of a lesion, I can ask a what if question saying, how should this lesion kind of change if it should be detected as some other type of lesion? And the model actually gives you evidence for that.
Yeah, that ability to query the model is kind of interesting. Could you talk a little bit about what opportunities a doctor has today, and maybe if you have any vision for how this will develop in the future? Will models become more conversational in some way?
Yes, definitely. So there are two aspects that I see here, right? So we write this paper and we submit this to a conference. And a couple of weeks after that is when a pandemic starts becoming very severe. And the immediate question that we had was, how do we repurpose this tool in the case of COVID-19? So it was a fresh problem which we had no clue about how to solve. And we get into conversations with doctors. And the immediate question they ask is, okay, there is an obvious ability of using this in screening. However, we still have other preferable screening mechanisms, PCR testing or other types of drug testing that people use. And while there is still a lot of promise in using chest x-rays as a screening modality, there is a bigger value to this. And the question they ask us, we are interested in understanding the influence of different interventions. And mathematically, this is basically a causal reasoning kind of a problem where so if I give this particular vaccine or this particular drug, how do I expect the patient to change or to progress or get worsened or whatever, right? And it's not a trivial problem to solve. And the second important problem that comes up there is it's not one type of data that they want to make this analysis based on, but a myriad of sources. For example, they want to look at their lifestyle habits. Do they smoke? Do they not smoke? Did they have a pneumonia before? Their health records, their subpopulation that they belong to, the place that they live in. And all these factors together, they want to load it up in order to build an introspection system. However, these mechanisms are extremely simple because these predictive models are tailor-made in some sense, where we take an image and we make a specific type of prediction that we ask the model to. So now taking this model and applying into this real world analysis, which is driven by a variety of control variables, which you did not even have access to while building the model. And how do you do that? And that becomes a very important challenge. And there are some extensions that we have done to this work where now we can. So basically, in a nutshell, the analysis is done this way. The doctor places an hypothesis. They say the patient gets better. The severity becomes higher. The doctor says a new type of infection comes up, and it's a hypothesis. Now, the hypothesis need not be placed in terms of one factor, which is the diagnosis state. Now, the doctor can place it based on a number of factors, their age, their gender, their smoking habits, and everything, and jointly drive this analysis. But it is still only one step forward, and we have a long way to go before enabling doctors actually interact with this. Because the doctors not just want better communication with these models, but they want the ability to keep inputting more and more additional information as they do the analysis. Because that's how a doctor makes a decision. They take into account 1,000 things in their head in order to come up with a single decision. And some of them are useful, some of them are not. Each doctor has their own personal experience with which they look at these factors. And how do we put all of that into an AI engine is kind of a very intriguing question.
Definitely, yeah. I mean, perhaps we'll get there, but there's going to be a lot of steps along the way, I would imagine. The reliability plots, which is something I encountered for the first time in this paper, seem to be a really great visual for helping someone maybe decide a decision question like, should we just trust and go with what the model has said, or should we escalate this to an actual doctor? And obviously, the model can help inform that by outputting its uncertainties, as we've discussed. But I guess I'm curious to hear your thoughts on the operational process. Is that a machine learning engineer's call to make, or a doctor's call, or how do we collaborate and get the most out of tools like this?
So it's a bit of both, right? The challenge as an engineer that we typically face is that how do we translate this information into a form that they can ingest into their common decision making process? So, for example, none of this is still standardized enough. So, for example, if you show an X-ray to a doctor, all doctors have come to a common way of or a standard way of interpreting X-rays. And that's being followed, that's standardized. However, with these interpretability tools, there is no still a standard process in which they should ingest this information in order to make a decision. So the big challenge we are typically facing is, for us, it's very easy to say uncertainty as a quantity. But how do you visualize uncertainty? How do you show uncertainties when there are uncertainties on more than one variable and you want to show it to a person? So there is a fundamental challenge of communicating this in a way where we do not lose the essence of the information. For example, there are many tools that are tried in order to simplify uncertainties into understandable encoding while losing a lot of information. On the other hand, if you show these complex mathematical representations, it's very hard in order to get a practical or actionable insight out of it. So I think it is an ongoing conversation between people in the domain, people who do machine learning and AI, and people from visualization. It is kind of an ongoing conversation between these parties together in order to build useful tools in some sense, right? And we are increasingly participating in that. So there are a lot more events and workshops and seminars and conferences happening where this particular dialogue is becoming stronger and stronger. And that interdisciplinary and diversity is essential in order to make this into a reality.
One of the things that really got my attention in the paper is the ability to generate those counterfactuals. I guess maybe as we kind of wind up a little bit, could you talk a bit more about how you envision someone using that? Is that maybe a doctor gets 10 other examples, like, oh, similar also? Or do you have any thoughts on the best way to present that?
Yes, so I think while example driven analysis has been around in the vision community and in general medical imaging community as well for a while, where prototypes and anomalies and novelties are being analyzed, I think a key opportunity that this work brings in is that the doctors can produce hypotheses in order to generate these counterfactuals. For example, I mean, let me give a concrete example with the COVID thing that we have recently done, where what we are able to do now is I want to understand how the COVID infection becomes severe and compare it with respect to say how a normal pneumonia would have manifested in a patient, okay, in the same patient. And what we find is we find signatures that are significantly different in terms of how the lung opacities kind of manifest, the symmetries between them, and all these kind of very subtle differences that kind of crop up between these two infections. The way we did this analysis is we did not give an example. In fact, we take a healthy patient and generate counterfactuals to produce pneumonia like symptoms versus COVID like symptoms. And in that scenario, what we find is a hypothesis is the most easiest way in which the doctor can interact because it is in the language that they understand. And that's going to become more and more central or integral part of the next generation of interpretability tools, where it's going to be hypothesis driven, where you are not just going to show how a model works. You are not just going to show how a model does in every single scenario that you could think of. Instead, you allow the expert to come in and actually ask questions. And framing hypotheses in terms of the clinical factors that they understand and they care about is the most easiest way.
Yes, that makes great sense to me. I could see where a doctor would want to say, clearly this person is sick. Do they have COVID or do they have something else?
Correct. And more interestingly, so this person was a young patient, okay? And you can ask a question. If this person was slightly older, would it be very different if the comorbidity was like this? So there are so many factors people want to bring into the analysis, right? That gives them a complete picture into is there age related characteristic? Is there gender related characteristic? Is the subpopulation you belong to, which region you come from, are there influences? And you want to start these intricate relationships between these multiple factors.
Yeah, there's a lot of exciting opportunities there.
Oh, definitely. So it's a question that is important for us to bring up is there has not been enough methodological studies in the clinical community in order to standardize and evaluate interpretability techniques. And that is something that we should bring about, right? How much are these tools being currently used? I mean, there are cool papers being written up. So do doctors, even who rely on diagnostic tools, do they actually use these interpretability techniques in their analysis pipelines? The answer is actually no. So this is still an engineer's job in order to convince a doctor why this model is good. However, there is no use beyond that into their day-to-day healthcare analytics pipelines, and which is where we need to be. And the big question that we face as a community, and that's something we should definitely discuss, is we should systematically think about ways of evaluating the quality and fidelity of explanations in this particular healthcare domain, for example, and try and see how a community-wide understanding of what are the grand objectives. So we need to set up grand goals of what is actually going to be eventually useful. And that's currently missing. And that's something I want to add.
Well, very good ambitions. Maybe to wind up, could you talk a little bit more about what you're most excited about over the next couple of years?
So now that we know how to scale and build really large scale machines, we know how to ingest big amounts of data. I think we are down to the key questions of building domain aware models. While these generic tools have been extremely powerful and have gained a lot of interest, we are starting to talk about specific domain challenges and interpretability being one of them. But lack of labeled data is being another one of them. So self-supervision is turning into an important idea. If explainability is integrated into the self-supervised modeling pipelines, it could produce a lot of insights. So there is not enough labeled data, and we want to use self-supervision. We are trying to synthetically generate pseudo tasks from the data, unlabeled data, or whatever data that you can access. If you make explainability as a design objective as part of this whole process, the practitioners can get a lot out of it, of how the model even thinks what is the best task to solve in order to build a face detector. And explainability, I expect it to play a significant role in it. And I'm generally excited about domain aware, and particularly all these sciences, of incorporating whatever knowledge that they have and the feedback that they can potentially provide into building next generation of AI tools.
Well, very neat. Yeah, I am excited about those areas as well and look forward to following advancements as they come. Jay, this has been really great. Where can people best follow you online?
They can follow my Twitter handle, it's jjram7, and my website at jjthiagarajan.com.
Excellent. We'll have links to that in the show notes. Thanks for listening to Data Skeptic Interpretability. Quick reminder, we've got the live stream coming up May 30th, 2020. Please join us. It's going to be a lot of fun. More information at dataskeptic.com/live. Our guest today was Jay Thiagarajan. Our theme song is Number 5 by Big D and the Kids Table. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. I've been your host, Kyle Polich. Be careful of these relaxing rules. The second wave is coming. Stay safe, everybody.